Hello again. Today we're going to take a look at an application of the derivative that's called related rates. And basically these are word problems or applications that have a situation where two or more variable quantities are related. And our goal is to try and figure out the relation between those quantities and then how they are related with respect to time. So best way to I think, to look at these problems is to just kind of dive into them and see an example, then talk about a process, and then just look at some more examples of it. So here we're told to suppose a snowball is melting uniformly such that its volume is decreasing at a rate of 2 cubic inches per hour. How fast is the radius changing when the radius is 4 inches? So here's, if we kind of look at this problem, well, first, we've read through it, and hopefully we have some understanding of the problem. A snowball is melting, right? And how is it melting? It's melting at a rate. Let's look at this rate. It's melting at a rate of 2 cubic inches per hour. So it's melting with respect to time. So the volume is changing with respect to time. We could turn that into notation. We could turn that into calculus notation. The volume is decreasing at a rate of 2 cubic inches per hour. We could say, well, that's the same if we think of V as the volume. So if we let V be the volume, then this is telling us dV dt, the volume with respect to time, the change in volume with respect to time, is decreasing negative 2 cubic inches per hour. How fast is the radius changing? How fast is the radius changing? All right, well, again, let's sort of take that into notation. How fast is the radius changing? If we let r be the radius, we want to know dr dt. That's what we're trying to figure out. What's dr dt? What's the change in the radius with respect to time? How fast is the radius changing? When the radius is 4 inches, that gives us a specific value. So now we have to bring in something from the outside. We have to know something about the relation between the volume of a snowball and its radius. So here we have to make an assumption. Let's assume a sphere. Let's assume that we have a perfect sphere, because then I can bring in some knowledge from geometry. If we have a perfect sphere, then I know that the volume of a sphere is given by V equals 4/3 pi r cubed. I know that from geometry. So notice now that I have the volume and the radius related. It should seem reasonable then that the rates at which the volume and the radius are changing respectively should also be related. But now if I think about this, I want to know I know something. I know something about the change in volume with respect to time. I want to know something about the change in the radius with respect to time. So what I'll do is I will differentiate implicitly with respect to t. So let's calculate now d by dt of both sides. Let's find d by dt of both sides of this equation. So d by dt of the volume should be equal to d by dt of 4/3 pi r cubed. Alright, well, d by dt, the derivative with respect to time of the volume, is just dv dt. Now let's see, we have 4/3 pi r cubed. Well, 4/3 and pi are both constants. I can sort of bring those along. So I have the 4/3 pi. Then d by dt of r cubed, that would be 3r squared times dr dt from the chain rule. So now if we simplify this a little bit, the 3's reduce. So then dv dt, the change in volume with respect to time, is then equal to 4 pi r squared times dr dt. So now I'm trying to solve for dr dt. Right? I'm trying to solve for this piece. I need dr dt, and let's see, it depends on dv dt, which is known. It depends on and it depends on r, which is also known. Alright, so let's take that. Let's make some substitutions. dv dt is -2 cubic inches per hour, and that's equal to 4 pi. Now r is 4 inches, right? We're told that the radius at that moment is 4 inches. So let's use that. 4 pi times 4 inches square, r squared, times dr dt. So if we simplify this a little bit, we've got -2 cubic inches per hour is equal to 4 squared is 16, 16 times 4, 64 pi, and let's see, we'd have inches square times dr dt. And so now I'll divide through both sides of the equation by the 64 pi inches square. So then dr dt, and let's see, -2 over 64 pi, that's the same as -1 over 32 pi, and the units on that would be inches per hour, since the inches square reduce out. So inches per hour. So dr dt, at that moment, when the radius is 4 inches, the change in the radius is -1 over 32 pi inches per hour. And those, if we think about it, if we were starting with a snowball and the volume, right, if the volume of that snowball is decreasing, it should seem reasonable that the radius is decreasing, right? It's in a sense, it's melting off, but the size of the sphere should be decreasing. So the radius should be decreasing. That negative makes sense. Also notice how, in working with the units seem to make sense. Right? If the radius of a sphere is in inches, then if we're differentiating with respect to time, the units on that dr dt, the change in the radius per time unit, should be inches per hour, and those units matched up. So that was an idea of how to approach these problems. And let's kind of formalize that a little bit. Here's a general approach, and here's basically what I did. I read through the problem, and I tried to visualize it. This one was fairly straightforward. It was just a sphere. I didn't really need to draw a diagram for this one, but I could have. But we'll see some later exercises where a diagram is going to be very useful in helping us understand the problem. I determined the variable quantities. What was changing in that problem? The volume and the radius were changing. They were variable quantities. Were there any constant quantities? Well, there weren't any constants in that problem. Just the two variable quantities. I mean, we had the 4/3 and pi from the formula. Those weren't really constant quantities. Those were just numbers, parameters from the formula itself. Relate the variable quantities. The relation was, in this case, the volume formula. The volume was 4/3 pi r cubed. That was the relation. Then I differentiated with respect to t for time. We will usually do that because most of these types of problems we're thinking about how variable quantities change with respect to time. But it doesn't have to be with respect to time. That just happens to be what we normally see. And then finally, I substituted the known variable quantities, the values. We knew at that moment that the volume was changing with a certain rate, and we knew the radius was at a certain value. And so we were able to then solve for the unknown quantity. So that's a general approach to these. Now, the only way to get better at these is to do them. You have to practice them yourself. So for each of these exercises, I'm going to read it aloud, and then I'm going to ask you to pause and to try it on your own before I do it. It's important to try these, and if you make a mistake, that's okay, as long as you learn from the mistake. Water is leaking onto a floor, creating a circular puddle with area that is increasing at the rate of 3 square inches per minute. How fast is the radius of the puddle increasing when the radius is 10 inches? Read through the problem. Think about what are the variable quantities. Can you take these phrases and translate them to calculus notation? Can you come up with the relation between the variables? Differentiate with respect to t and see if you can solve it. Now would be a great time to pause to try this one out on your own. So here's what I would do. The water is creating a circular puddle. Circular, okay? I know some things about circles. With area, I know how to talk about the area of a circle. Let's see what we have here. The area is increasing at the rate of 3 square inches per minute. The area is increasing. dA dt, the change in area with respect to time, is 3 square inches per minute. How fast is the radius of the puddle increasing? I need to find dr dt when the radius is 10 inches, when r equals 10. 10 inches, I should be more specific here. Alright, so can I relate the variable quantities? How is the area related to a radius for a circle? Alright, well, we know from geometry that the area of a circle is pi times the square of the radius, pi r square. So then I will differentiate with respect to time, both sides. So then dA dt is equal to pi times 2r by dr dt. Now, look at what we have. We have dA dt here, and I know that value. Pi is constant. 2 times r. We know r. We don't know dr dt. We have all of the pieces of this puzzle except for the one we're trying to solve. That's awesome. We got 3 square inches per minute is equal to pi, well, let's just say 2 pi times 10 inches times dr dt. So then dr dt would equal 3 square inches per minute over 20 pi inches. So then dr dt would be 3 over 20 pi, and then inches square per minute divided by inches, that would be inches per minute. That seems reasonable. The radius should be, if water's leaking onto the floor and the area is increasing, it should seem reasonable that the radius is also increasing, right? And we do end up with a positive value here for the dr dt. The radius is in inches, so it should seem reasonable that its change is in inches per minute. So here's the solution. dr dt is 3 over 20 pi inches per minute. A light is on top of a 15-foot pole. A 6-foot tall man is 8 feet from the pole and walking away from the pole at a rate of 2 feet per second. At what rate is his shadow increasing? For this one, I think a diagram is going to be particularly useful. And in setting up this problem and creating the relation, I'm going to use similar triangles. Now would be a great time to pause. Try this one out on your own. Alright, so I'm going to draw a diagram for this problem. Let's say here's the ground, and here's the light pole. There's the light pole. And so, and here's the man, and I'm not a good artist, so I apologize for drawing stick figures, but that's probably the best I can do. The light comes down, hits the man, creates the shadow. There's the shadow that's being created from the light. Now, it's on top of a 15-foot pole. That's not changing. That's not a variable quantity. What is changing? The shadow is changing as he moves away, and his distance from the pole is changing. At the moment, the distance is 8. But that distance is not constant because we know that the person is walking away from the pole. So let's call that distance from the pole, let's call it d. It doesn't really matter what variables you call these things. We also have the height of the man. Alright, and let's assume that that's not changing. The height of the man is exactly 6 feet. That's not going to change over the short term. So now the way I see this, there are 2 triangles. We have this one triangle here that I just marked in blue. We have this one triangle, and then we have a larger triangle, which I'll mark in orange. Now, if we assume that we don't even need to make any assumptions here. I was going to say, if we assume that it's at a that the pole's at a right angle to the ground, it doesn't really matter. We have similar triangles here. So let's use a proportion to create the relation. All right, so then using similar triangles, I could say that S is to 6. S is to 6. The length of the shadow is to the height of the man, as the total length, this total distance, as D plus S is to 15. So from similar triangles, here's a proportion that relates the quantities. So then 15S is equal to 6D plus 6S, which means that 9S is equal to 6D, or S is equal to, dividing through by 9, S is equal to 2/3 D. So in this case, we were able to easily solve for S explicitly. So now, if we kind of go back to this, what do we know? We know that the man is walking away from the pole at the rate of 2 feet per second. So that's a change in D, right? D is the distance from the pole, and that's what's changing, right? That's what we have the value for. So we know that D poor choice of variable, sorry about that, dd dt, the change in that distance with respect to time, is 2 feet per second. Alright, so now let's take this. We know that s is equal to 2/3 d, and let's calculate d by dt of s, and that would be equal to d by dt of 2/3 d. So then ds dt is equal to 2/3 d dt. So then ds dt is equal to 2/3 times 2 feet per second. So then ds dt, the change in the shadow with respect to time, is 4/3 feet per second. Alright, so here a diagram was particularly useful in helping us solve this problem. So here's another problem where a diagram is going to be particularly useful. The top of a board that is 10 feet long is sliding down a wall. At the instant the bottom of the board is 4 feet from the wall, the bottom is sliding away from the wall at a rate of 2 feet per second. At that instant, how fast is the top end sliding along the wall? So now would be a great time to pause, try to draw a diagram for this problem, and see how you could approach it. Alright, so I hope you took a few moments to try and draw something for this. Now, if you haven't seen this problem before, it might be hard to conceptualize what's going on. Fortunately, Desmos, there seems to always be something on Desmos for these, Desmos has a good visualization of this problem. So here's a visualization, and here I have this ladder length that's 10. And so what's happening here is as we move the ladder along the ground, as we slide the bottom of the ladder, notice what's happening to the top of the ladder, assuming that it stays in contact. Right? So as I move the ladder along the bottom of the ladder along the ground, the top of the ladder slides down. And so then the idea is, at a certain moment, at this moment, how are the two quantities related? So if we think of the distance here between the base of the ladder and the wall, and if we think of the distance between the top of the ladder and the wall, how are they related? And then how are their rates related? Alright, so notice that the top of the board is 10 feet long. That isn't changing. Alright, that's constant. Alright, so let's think about this. There's our wall, there's our ground, here's my ladder, or board, and that's a set 10. Let's assume that they're at a right angle, that the wall and the ground are at a right angle. So we have two unknown quantities, really. We don't know, well, I should say we have two variable quantities. The distance between the base and the wall, let's call that x. The distance between the top and the ground, let's call that y. So then, now that we have this diagram, at the instant the bottom of the board is 4 feet from the wall, the bottom is sliding away from the wall at a rate of 2 feet per second. The bottom is sliding away at 2 feet per second. So let's see, at the instant the bottom of the board is 4 feet from the wall, when x is equal to 4, and dx dt is 2 feet per second, how fast is the top end sliding along the wall? Find dy dt. All right, so using the notation that I've built into this problem and the diagram, that's what we're looking for. When x is 4 and dx dt is 2 feet per second, find dy dt. All right, well, we have to relate the variables. How are x and y related? Well, I know, since I have a right triangle, that x squared plus y squared is 10 squared. That's a Pythagorean theorem. So then I'll apply the differential with respect to t, dx dt. All right, I'll move down here. All right, so then d by dt of x squared plus y squared, that would be, implicitly, that would be 2x times dx dt plus 2y times dy dt. And 10 squared is 100, so its derivative with respect to time is 0. Now we're asked to find dy dt. I'm going to solve this for dy dt. So then dy dt is negative 2x times dx dt divided by 2y. All right, so I moved the 2x dx dt term over by subtraction, and I divided by the 2y. All right, and we can simplify that. So dy dt is equal to negative x over y by dx dt. So now let's think about that. What do I know? I know x is 4, and x is 4 feet. I should be more specific. X is 4 feet, and I know dx dt is 2 feet per second. I don't know y. I've got to figure out y first. Now to figure out y, I can go back to the formula. So let's think about this. I need y when x equals 4. All right, well, if x is equal to 4, then 4 squared plus y squared is 10 squared. So 16 plus y squared is 100. Y squared is 100 minus 16. That's 84. So then y has got to be positive here, right? That's the only value that makes sense here. Y is the positive root, square root of 84. Or if you wanted to simplify that, that's what 4 times 21, 2 root 21. That's not too important. And I guess that would be in feet. Right? Y should be a distance in feet. So, what do we now have? Then dy dt would be negative. Now, x is 4 feet. Y is 2 root 21 feet. Dx dt is 2 feet per second. All right, so if we simplify this, dy dt is negative. The 2's reduce out. The feet reduce out. Negative 4 over root 21 feet per second. Negative. Let's think, if we think about this problem, maybe let's go back to the Desmos for a second. So dx dt, if x is increasing, if this distance is increasing, what's happening to y? Y is decreasing, right? If x increases, y decreases. That should seem reasonable on the diagram. And that's what we got here as the result. If x is increasing, if dx dt is positive, it turns out that dy dt is negative. And it turns out to be specifically negative 4 over root 21 feet per second. All right, so we have several other problems to look at, but this video is getting a bit long. So I'm going to stop this video now and I'll pick back up with the other exercises on another video. All right,